By definition, stoichiometry is a mass relationship among reactants and products in a chemical equation. Remember, reactants are on the left-hand side, products are on the right-hand side. And we know that what we have to do before we can even do any stoichiometry is that we must have a balanced chemical equation. And that goes back to the scientist Anton Lavoisier. A couple of some key terms you need to know: limiting reagent and excess reagent. Limiting reagent is the key reagent because everything is based upon the limiting reagent. The limiting reagent, just like the name implies, limits everything. Not only does it limit the other reactant, but it also limits the products that can be formed. The excess reagent is the reagent that you have more than you need. An analogy here is a cheese sandwich analogy. We'll say to make one cheese sandwich, it requires 2 slices of bread and 1 slice of cheese. And if I gave you 8 slices of bread and 6 slices of cheese, how many sandwiches could you make? And you realize that your 8 slices of bread is going to be a limiting reagent, and it's going to limit you to a maximum of 4 sandwiches. That's your theoretical yield. That's the maximum in the perfect world. Your limiting reagent was the bread. Your excess reagent was the cheese. The cheese was told you could make 6 sandwiches. The fact is you only can make 4. Also, we know this: based upon a limiting reagent, not only did the limit reagent limit me to 4 sandwiches, it limited me to using only 4 slices of cheese. Therefore, I had 6, I used 4, I had 2 slices of cheese in excess. Some more key terms you need to know are theoretical yield, actual yield, and percent yield. Theoretical yield is by calculation on a piece of paper. That's what you're going to be doing every single time. By default, theoretical yield is a unit of grams, and it's a grams of a product. So with this, you will always be going after theoretical yield. I can give you actual yield. Actual yield is what you actually get when you carry out the actual experiment, and that's what you did in lab. And a percent yield is taking your actual yield, your score, divided by theoretical yield, the maximum possible. So it's your score, what you got on the test, out of what the maximum points on the test, multiplied by 100. That's all you're doing mathematically. Also, I could give you percent yield, by the way. If I gave you the percent yield, you solve for the theoretical yield. To get the actual, we'll say it's 90% yield, you would take 90% of your theoretical. That means 0.9 times your theoretical would be your actual. I could do that as well. The key aspect for stoichiometry is that of the roadmap. On the left-hand side, you see right here, in the left-hand side A, that's your starting point. You have 3 places you can start with a problem. You can start with a mass, you can start with anything, which I refer to as atoms, molecules, forming the units, or you could actually start at the mole. So where you start is important because that dictates what your first step is. If I start with mass, I have to get back to the mole, so my first step is molar mass. If I start with atoms, molecules, or forming the units, or particles, then my first step is Avogadro's number, because once again I have to get back to the mole. And both molar mass and Avogadro's number are equal to 1 mole. Now here's a new part, and now what we can do when we get back to the mole, we can use the coefficients in the balanced chemical equation to move anywhere we want within the balanced chemical reaction. We can go from A to B, A to C, A to D, D to C, D to B, D to A, and go forward and go reverse. It doesn't matter. But where I'm starting is on the left-hand side, where I'm going is on the right-hand side. So I'm going to B. And then once I get to moles of B, then it's a copy and paste. To get from moles of B and go back out to mass, using molar mass if I wanted to, I could actually go out to atoms, particles, forming units, molecules if I want to, but that'd be using Avogadro's number. So we really see that there isn't a whole lot going on here. There's actually only 3 conversion factors. That's molar mass, Avogadro's number, and mole to mole ratio. So it really is have to understand, your left hand is what you have at the beginning, what number are you starting with, and on the right hand side is what are you solving for. If you pay attention to that with every single problem, you're going to be set. The first problem we have here, we have calcium reacts with oxygen to form calcium oxide. If you were given 80 grams of calcium, the question is then, calculate the theoretical yield of calcium oxide, and then how many moles of your excess reagent are used. So first of all, you always need a balanced chemical equation. It's a 2 moles of calcium to over 1 mole of oxygen yields 2 moles of calcium oxide. In this situation, I also understand my limiting reagent is calcium. I don't know anything about my oxygen, so I'm safe to assume that's my excess reagent in that situation. So again, calcium is my limiting reagent, that's the value I have. Oxygen is my excess reagent, I have more than I need. So the first problem asked me to solve, well, once my 80 grams of calcium is used up, because that's my limiting reagent, once it's used up, the whole reaction stops, how much calcium oxide can I form? So I start with my limiting reagent. I got my 80 grams, okay? I got it from the problem. Now I want to get, first step here is molar mass. We go back to the roadmap. We see that the first step here, you go from mass to moles using molar mass. And we get molar mass from the periodic table. Once we get back to moles, then I'm going to go from moles to moles using the mole to mole ratio in my balanced chemical equation. And then I'll head back out to mass using molar mass. But this time I'm on calcium oxide side, so I'm going to use the calcium oxide molar mass. So let's go back to the problem. So at the situations, we have 1 mole equals 40.08 grams of calcium. 1 mole equals that, segment moles or grams, grams or moles, it does not matter. I put moles over grams for one reason only, so my grams of calcium cancel out. Now I'm at the mole, but I must move across the river now, that's via the mole bridge. So I'm at 2 moles of calcium and I'm going to 2 moles of calcium oxide. That's where I'm going. So it's a 2 to 2 ratio. I can simplify that to a 1 to 1 ratio if I so desire. The last step is I need to now get from moles of calcium out to mass, once again molar mass. I know that 1 mole equals 56.08 grams, so I can put moles over grams or grams over moles. But in this situation I need my moles to cancel out, so I put moles over grams because I'm moving towards grams of calcium oxide. Mathematically, all I do is multiply across 80 times 2 times 56.08 divided by 40.08 divided by 2 equals. My answer will have 3 sig figs because of the 80. That's what we call your theoretical yield. That's the maximum of that product that can be formed in calculation. That's actually calculated. Now I want to know, well, how much my excess reagent was actually used. So I want to know how much oxygen was used. Well, to figure that out, again, I start with my limiting reagent. Because my limiting reagent, once the 80 grams runs out of my calcium, not only did it limit how much calcium oxide I can form, but it also limits how much oxygen I can use. So my first step on the roadmap, I'm going to get from mass to moles. Going back to the roadmap, I'm going to go from mass to moles of calcium. But now I want to go to moles of oxygen, and I'm done. That's all the problems take me to. I'm going to moles of oxygen. So in this situation, I go first of all molar mass, which I've already done up above. I know the molar mass. But moles over grams, so my grams cancel out. And then I'm going from 2 moles of calcium to every, now I'm going to oxygen, so I'm going to 1 mole of oxygen. I'm done. That's all the problem asked me to get is moles of oxygen. So 80, there's nothing to multiply by, so 80 divided by 40.08 divided by 2 equals, and 3 sig figs. My answer ends up being 0.998.